Today we're going to build a bass overdrive pedal, or actually we're going to start the design process building one. We're going to go all the way through start to finish, from concept to finished product. So I have this overdrive and it's been designed for guitar. I like the sound of a Les Paul into a classic Marshall tube amp, and that's what this is supposed to replicate. And to my ears, it sounds indistinguishable from the Marshall Overdrive. I have some demo videos on that if you'd like to hear it for yourself. But that's also a pedal. It works on bass, but it has a high pass right in the beginning of it, so it's not ideal. My brother is a bass player and he wants an overdrive that is made specifically for bass. It doesn't mangle his bass tone. And he likes the sound of this overdrive, but because of that high pass, he loses all of his bass. He has to turn the damp knob all the way up, and I don't know what he does with the bright knob, but there's just not enough bass in it for him, which makes sense. It's a guitar pedal. So we're going to look at this design that I've started for putting together a bass pedal. And you'll notice I've written a lot in cursive, and that's just me. I like to write in this book in cursive because we never use cursive anymore. So I like to make sure I get practice in writing it, at least sometimes. So the idea here is a two-stage overdrive, switch 1, switch 2. And the switch 2 has two knobs corresponding to it, which is the secondary gain and an extra high boost. And then switch 1 is global for the entire pedal. So that's kind of what these boxes indicate. And this is not a final design for the enclosure. This is just for illustrating the idea. So we'll have the main overall level, a high EQ, a low EQ. Both of these will be boosts. They won't cut, at least they're not planned to cut. And then there's the gain 1, and then turn on gain 2, we have the gain 2 knob and the tone knob, which is again a high boost. So switch 1 controls the whole pedal, switch 2 controls the secondary gain section, and the first LED is orange and the second is red. This is at the request of my brother. This is kind of his signature pedal, so to speak. So I'm trying to build this in a way that he is going to really enjoy using. So then whenever the entire pedal is off and the orange LED is off, if the gain 2 is on, this red LED is going to blink or pulsate at a lowered intensity. That way you'll know when you turn the pedal on, am I going to get the full boost or am I just going to get the gain stage 1. So then we'll look at a simplified block diagram here. And given this circuit topology that I'm going to be going through, it's very high gain. So it's always buffered. That's because I've had an issue with a lot of metal in the switches and in the jacks acting as antennas if it's not buffered as soon as it can be. So this buffer is right after the jack. So it's buffered bypass. And so we go on to the switch, which is just a straight bypass, just like a regular true bypass, but it's buffered before it goes anywhere, even into the switch. And then so we have our signal path right here. And this is how the low EQ knob is going to be implemented. First we have a buffer. These are both buffers. Just keep these two sections isolated from each other. they're both buffered. And we have a mixer, and I know I'm probably not using the right symbols, but it's a simplified diagram. And we have an amplifier with a low pass and positive feedback. So by adjusting the gain here, we'll adjust how much of a low boost comes out the other end. So this gain control here, it might really be a level control going out from this section into the mixer up here. Because if we vary the gain right here, we might also vary the positive feedback, which will not be desirable. So this may end up being more of a fixed gain scenario where we can variably mix it in up here. I think that'll probably be easier to manage. And then so for the main signal path here, we have our buffer, and then we have switch 2, switch 2A and switch 2B. And this is just the secondary gain, the gain 2. So we have our gain control here, and we also have a high pass filter right here. This is going to be our high EQ, or no, I'm sorry, this is the secondary. And this is the same sort of high boost topology that is in my imposter overdrive circuit. So then here in the main gain section, we have the same exact thing with the high pass filter and the positive feedback for the high boost. And then we're going to go through a low pass filter. This will get rid of all the harshness that exists in a clipped signal. And then finally go into a mixer and a buffer and out again through the switch to the output. Now this is very simplified because in the real world we're going to have the LEDs to control what the switch is. We're going to have the timer associated with making this LED blink. I'm not sure what kind of oscillator we're going to use yet, if 1 or 2 transistors will do it, or if I need to use a 555 timer, or even if a op-amp based integrator will be good with for that. Now with that out of the way, we will get started laying the groundwork for that circuit on a breadboard. But first, let me tell you about this video's sponsor, me. If you like to design electronics like me, chances are you're familiar with the process of reading datasheet after datasheet, just trying to figure out which component you're going to go with. While in that process myself, I thought up Datasheet Assistant, a tool created to save you time in the component selection process, and even while referencing the datasheet for a component you've already chosen. It's a tool that I've just recently launched with the aim of making the latest AI models truly useful for electronics engineers. Most applications of AI require you to put your blind trust in it or bend over backwards to verify its accuracy, defeating the purpose of using it in the first place. With Datasheet Assistant, you upload your datasheet, ask questions about it, and you get an answer, a quote from the source, and a link to scroll to that spot instantly within seconds, leveraging the utility of AI while avoiding the pitfalls. And this is only the beginning. At initial launch, it's like Control F on steroids. But there are more and richer features to come, including comparison between multiple datasheets, giving you the ability to consider multiple components at once in a matter of minutes. If you'd be interested in this tool, want to support its development, or just want to support me, head over to datasheetassistant.com and sign up for $20 per month. Now back to the video. So for my buffers, I like to use discrete JFETs. And this is a J111, but it's not too important what you use. I just like it because JFETs are high impedance on the input, relatively low impedance on the output, and they are very easy to bias. So I'll do one thing here first and tie together the rails on my breadboard. Now this specific transistor, the pinout is drain source gate. In the buffer configuration, we'll just tie the drain high. The source is going to be our output. I like to use a 10K resistor to ground. and the gate is going to be the input. I usually bias that with a 1 mega ohm resistor to ground, but this is for a bass guitar. I want to bias that with, or rather, I want the input impedance of this circuit to be 2 mega ohms rather than 1, which is the typical value chosen for a guitar. Generally though, for bass, we want that value to be a little bit higher. Here they are. So for this first buffer, I'll do a 2 mega ohm input. After that, I'll generally stick to the 1 mega ohm. And then for these coupling capacitors, to just block the DC, I like to use 1 microfarad. Anything less, and it becomes a little bit difficult, you might say, to keep all the bass frequencies, especially for a bass guitar. Anything higher than that's not particularly necessary, but not harmful either. Alright, that's the first buffer done. Now let's take a look here at our block diagram, see what we want to do. For this, I'm not going to implement the switches yet. I just want to get the sound in the right ballpark. So I'm putting together this breadboard for my brother to test. So I would like to get all 6 of these controls implemented in some way, and all of this circuit and this bypass for this secondary part. To start with, I will probably just make that jumper based. So we've got our main buffer, and then we need 2 more buffers after the switch, which again are just to separate this from all of this, to keep them from interacting. So we'll build 2 more of these buffers, identical, except we will bias them with a 1 mega ohm instead of 2 mega ohm resistor. Now some people can't stand for their resistors and wires to stick up off the breadboard like this, and I understand that for noise reasons, but it doesn't end up being very practical for why the breadboard exists. And in low frequency stuff like audio, it's not as big a deal as you might think. It does matter, but we're testing. We're not building the final product on the breadboard. Now, because theoretically these JFETs should bias to the same place, I'm going to start by not using a separate capacitor on the inputs of both of them. I'm going to use just one. If we have issues, I may experiment with going ahead and using both, but I don't think we'll need both. Now on the outputs of these, we'll definitely want to be perfectly referenced to ground, the best we can anyway. So we do want capacitors on the outputs, because the next stages are quite likely going to be directly feeding to the inputs of some differential BJT amplifiers. And that is the way I'm able to have such a high gain circuit without having an obscene amount of noise. I use MOSFETs for the clipping, but for the bulk of the gain, I just use regular old 2N3904 NPN BJTs. And they're not anything special, they're just general purpose. So I could probably achieve lower noise if I bought lower noise transistors, but I haven't really had that become an issue. And I will probably need to reference my schematic for the Imposter Overdrive so that I can not have to reinvent the wheel as far as that overdrive goes. But since I'm going to have two separate gain stages, I will need 2 transistors per gain stage. And because I have 2, I will actually have 4 gain stages. 2 clean BJT gain stages and 2 clipping MOSFET gain stages. And they're all differential. So the differential gain stages are going to need a current source, which I will implement with a basic current mirror. I need to restock my little tray down here. So this is the raw design process. It's unscripted. I have one idea. I realize, wait, no, that idea won't work. Let's do this instead. And it's iterative. So I have my 2 gain stages. All this would be a lot easier if I just decided to use op amps for all the clean gain. I just really like the idea of using discrete transistors. Okay, I think what I'm going to end up doing is use differential amplifiers everywhere, but for the secondary gain, I'm just not going to be able to sum them up. I'm going to treat it as if it's single-ended, but I'm going to put the input into one side, and I'm going to take the output from the other. That way it doesn't invert. And whether or not the signal inverts, it doesn't truly matter. I just don't like the idea of inverting the signal, so I try to keep it in phase with the input signal the best I can. So that means we are going to have 1, 2, 3 differential gain stages, and both of these are overdriving gain stages, which means we're going to end up having 5 gain stages, because I'll have the differential MOSFETs for overdrive and I'll have the differential BJTs for clean gain, and that'll be on both of these. These filters are going to go in the clean side, in the clean stage. The overdrive is just going to be fixed gain afterwards. Truly, all stages are going to be fixed gain. If there's going to be any variability to the gain, it's going to be in varying the level that goes into them. It's much simpler that way. It maintains a consistent operating point. So that means I'm going to need 3 BJT gain stages. Now I'm not really sure why I chose this particular MOSFET, the VN2222. I think it's just because it was cheap on Tata Electronics. And I can get the same thing through Mauser. But when I go to build this final design, these aren't the specific transistors I'm going to use. I'm going to use equivalents in SMD packages. Now I can get the 3904s in the SMD package, which I do use. The MOSFETs, I use a different one, and it's a T2N7002AK. And the specs are equivalent. They might not even have to be. I just made them as close as I could. I chose parts that are as close as I could to the ones that I designed with for really an obvious reason, to make sure that the production part that I decide to use isn't going to be different from the testing part that I'm using. And that way, hopefully, I only need one iteration of testing before I can go on to say this is a pedal that's ready for the market. So here we have our input buffer. We have our 2 buffers to separate the stages. And so Now I'm going to build I'm going to put the bass boost stage right here. I might actually need more space. I'll put the bass boost stage right here. Oh, I don't need the second overdriving stage. The boost stage just needs a clean boost. That helps a lot. I'm going to put the clean boost right here. I'll need one buffer for the clean boost. This will be the same. I'm only going to take one output from it. I'll need one buffer for that, though this might be buffered by mixing into the final signal. So I'll leave the buffer off of that for now. This will definitely need a buffer because the next stage it's going to see is another BJT stage. But we'll only need one since we are just taking from one of the outputs, not both. And so here's the next BJT stage. I'm going to move that up here. There's the next BJT stage. And I'm going to put a buffer in between that stage and the MOSFET stage. I did it the same way for the Imposter Overdrive. This section is going to be pretty much a one-for-one copy of the Imposter Overdrive. I need to make more space because I am going to need one op amp to sum together. I am going to need one op amp to sum the output from the differential stages, which helps with noise immunity. I don't use anything special for the op amps either. I just use these Texas Instruments TL08 amplifiers. This one's the TL08-2. As long as I don't need a second op amp, the final product is just going to use a TL08-1. So we're going to make sure this has power. That's another thing, is power. This circuit is going to be powered from a voltage regulator, which helps a lot with power supply noise immunity. I've found that out the hard way. But it also has the benefit of allowing to feed the circuit from 9 volts all the way up to 18 volts. The 18 volts it could get a little hot and could end up burning up the regulator. So I only recommend 15 volts. Yeah, I do need to pull up my circuit, just again so I don't have to reinvent the wheel. So since this is getting split into 2 gain stages, I don't need as much gain per gain stage. My Imposter circuit has 1 clean gain stage and 1 clipping gain stage. That clean gain stage will essentially be split up into 2, so I only need half the gain per stage essentially. So the only thing I'm really going to get to one-for-one copy over is the MOSFETs. Before I forget though, I need to get my current mirrors done. So for every differential gain stage, they need a current source. And so that is 5 gain stages. And then we're going to need basically the master current source, which the rest will be mirroring. So I'll just stick that right here. Actually, I'll put it right here so it's a little more out of the way, a little more obvious that it's separated from the rest of the circuit. And then for these 2 gain stages down here, I will put it right next to them. But I'll put it kind of in this back row almost, just so I can see that it's not one of the amplifying transistors. Just for ease of layout, it's not a necessity. And then for these over here, I'll just put them on the bottom section here, which is really the reason I wanted to leave that section open. All of these current mirrors just have their emitters tied to ground. The first one has its base tied to its emitter, and it is connected to the supply rail by a 510K resistor, which, if I remember correctly, was just chosen arbitrarily. These differential stages need their emitters tied together, so that compacts things a little bit. And the MOSFETs, make sure their sources are source, gate, drain is the pin out on these. All right, and for all of these mirrors of the current source, the collector ties to the emitters, and we're not using any ballast resistors, we're just tying directly. Ballast resistors can help with stability of the amplifier, but I found when originally designing this circuit that it wasn't necessary for this circuit. And the MOSFETs get the same treatment, except it's their sources, not their emitters. And then the emitters of these current mirrors just need to go to ground. Then all that has to be done with those is their bases all tied together. I'm going to try to stick to using these solid wires for that, because the stranded ones that I have are, well, they're these things. Especially the ones on the bottom there, they're not very reliable. They work, but not well. Again, if this looks like a noisy mess, keep in mind all we're doing is checking to make sure that this circuit is going to sound good. We'll denoise it the best we can on the breadboard, which will result in a very thoroughly denoised circuit once it's transferred to a PCB. Sometimes things do slip by though. Found that out the hard way too. Okay, so the current mirrors are done. Now before I put in the resistors for the differential amplifiers, I'm going to go ahead and get the buffers done, just because there's no calculation to be done. They're self-biasing. And these are buffers, aren't they? Yeah, these don't need a current mirror. Yeah, I got one too many current mirrors. Yeah, so these are buffers, drain, source, gate. So these drains can, the drains of these can be tied together. Less jumpers to worry about, because they'd be tied together anyway when they get tied to the supply voltage. I'm going to need to restock my mega ohm resistors as well. I've been going for 48 minutes. All right, let's take some of these. It's much easier to prototype with when they're pre-bent. Or maybe I'm just saying that. I'm just used to them being pre-bent, so I'm pre-bending them. I usually end up bending them in another way than they were pre-bent anyway, so it's fine. This makes them fit better in my tray though. So with these differential amplifier stages, I'm going to start with putting the collectors. I tied these collectors together. I need to tie the emitters together. These are the kind of stuff that happens when you haven't breadboarded in a while. Okay, I'm going to tie these collectors to the supply voltage with 100K resistors. In my original circuit I used 270K, but because we don't need as much gain in each stage, I'm using 100K just to start with. And I will do that for each stage, except for the bass boost stage. We don't need a crazy amount of gain there. We'll experiment with that. I'll probably start with 51Ks, because we still do want a little bit more gain there than is practical. And the reason for that is just so when you turn the knob up all the way to 10, it's a lot. Cover all the bases that way. All right, those are in. Now the original bias for this Both stages are biased to around 2.5 volts, give or take a little, from a single voltage divider. That might not be the best for these amplifiers. So that's going to be something else to experiment with. And I'm going to need to brush up on how to calculate gain for differential amplifiers without ballast resistors. Single-ended amps, relatively simple. Differential amps, also simple. It's just been a while since I've done it, so I don't remember how to do it. All right, these are our 51Ks for the bass boost stage. Now the nice part about using differential amplifiers for boosts is you can take the output from one side of the amplifier and feed it through a filter to the input of the other side, and you get positive feedback that way. Negative feedback works well if you want a reduction in gain, so if you want to make a notch filter or cut something. But if you want to boost something, positive feedback is what you want. You just don't want a gain greater than, I believe it's 3. So I won't deal with the output of this bass boost section yet, because I'm not sure yet if I'm going to need a buffer. I'll probably need a capacitor, but again, I'm not sure yet. I will need one on the input though, and it generally does help with noise if on the second side of the amplifier, if I'm feeding it from a single-ended source, if I just tie it directly to ground, it seems to help cancel out some of that ground noise if there's any there. So I'll do that. And I'll add the capacitor for the input. Now these will still need biased, but I'm getting the capacitors ready right now. This gain stage will be the same because it's fed from a single-ended source. Now I need to restock my 1 microfarad capacitors. I actually need to buy more of these. I'm low on them. There's going to be a capacitor between everything. Chances are it'll be necessary. But then that means we do have to keep in mind... Why did I spread these out? I didn't need to do that. We do have to keep in mind that we're putting together a bunch of capacitors in series, which we need to be careful when combined with resistance, especially because we're dealing with bass signals. We don't want to lose any of that low, roll off any of those lows. So now with the outputs of those, we're going to go into these buffers, and off the outputs of those buffers, we're going to go into the clipping MOSFETs. And on the outputs of those, we're going to go into the op amp to sum, or rather, take the difference between the two signals. If we were summing, we would just get 0 because they're differential signals. We're going to get the difference. So I would do that up here on this side, but it's a little bit cluttered. I'll do it down here on this side. So here we have this is the ground pin. We have the non-inverting input, the inverting input, and the output. And it's the same thing over here, but shifted over because this is the supply rail. I'm going to experiment with this, but in the design of the Imposter, I used 1 mega ohm resistors right here. So the non-inverting input is going to need bias to almost dead center of the supply. It needs to be just a little bit higher because its operating range is a little bit asymmetric. I'm going to feed that from a voltage divider of 10K on the low side and 8.2K on the high side. And that's what this resistor here goes to. And then the next two are going to go from between the output and the inverting input. And the last one will go from the inverting input, or rather from the differential amplifier, one of the outputs, to the inverting input. Through the capacitor first though, so we need to get that set up. I need to shift this over one hole. All right. So the last thing that really needs to be done with the amplifiers is the bias. Of course, the boosts as well, but I'm going to look at those as separate components. So I think we're going to finish today with setting up the bias for the op amp, because I'm not going to need to recalculate that. That's just a 10K low and an 8.2K high. Do I have any of those out? Doesn't look like it. I don't need them very often, so I don't typically keep them in the tray. Alright, and you know what? With these two clean gain stages having the same gain, I think they can have the same bias too, but I'll still deal with that next time. So what we've done here, we have our input buffer, and then we have our two, I'm going to call these isolation buffers. They just isolate the sections that come after them from each other so they don't interact. We may experiment with these to see if they're really necessary. And then we have here the amplifier for our low boost. And the boost is not there yet. This is just the amplifier. And then we have the amplifier for our boost section. This is our gain 2. And then we have the buffer for it. We're just taking a single-ended output, and that is the same for the low boost amplifier. And then we come back up here to our gain 1 amplifier. This one is going to stay double-ended, which is why we have two buffers here. They're going to go into there. I could have went ahead and wired that up, but I didn't, so we'll get to that next time. And then from there it stays double-ended. We're going to go into our clipping gain section, which is MOSFET clipping. The reason for that is it sounds a lot more pleasing. We get a lot less spiky, fizzy sounding artifacts than we do with anything diode based. So if we push these to clipping, it'll sound just like regular diode hard clipping, because that's kind of what it is. Not quite, but kind of. Because it's the same technology, they sound the same. I don't like the way it sounds. MOSFETs sound a little bit more like tube overdrive, or really, I would go as far as to say they sound identical to tube overdrive, because to my ears, the overdrive that I designed is indistinguishable from my Marshall tube amp. But anyway, that's not the focus of this video. And then from there we go double-ended into a difference amplifier, which is just an op amp set up as a difference amp. It essentially adds together the magnitudes of those two signals. It takes the difference between the two. And so that converts it into a single-ended output, which will then be taken through a volume pot and buffered one more time. Next video we'll probably implement the controls for that, which means adding the buffer and the volume pot. And then lastly, we have the current source and all of its mirrors for all of the amplifiers. So that is one source, 4 mirrors. And so in the next video, we're going to take care of the biasing for these amplifiers. And we're going to take care of the controls, which is going to include the boost circuitry as well. Much of which will be preliminary, because it will need to be tuned by ear. You can do all the math and get it perfect, but if it doesn't sound good, there was no point. You may as well tune it by ear, because you'll be doing that anyway. So if you enjoyed this video, where I go somewhat in depth with my breadboard design process, then go ahead and drop a like, leave a comment, hit subscribe. All that tells YouTube that people like the videos. It helps YouTube push it to more people, more like-minded people who like these videos just like you do. So I hope you guys have a great rest of your day.